Alright, youngsters, last section of this unit, we're finally going to take some of these rational equations and we're going to solve some word problems with them, for some of those real-life situations here. So let's have a look. So we're just going to jump into some examples and you can get a sense of how this is all going to go down. So the first one here is a speed, time, distance kind of question. So Jerome rows his boat 24 kilometers downstream and back. When the average speed of the current is 2 kilometers per hour, so the water's moving, he can complete the trip in 9 hours. And then what's his average rowing speed in still water? All right, so the first thing I'm going to do is I'm going to kind of make some sense of what I have here. I'm going to draw a little picture. Right? So here's a nice river. Look at that beautiful river. We know he's going to start right around here. It's going to end right around here. We know that the distance between here and here, I'm going to interpret this as 24 kilometers. I know it says 24 kilometers downstream and back, but I think it's 24 kilometers downstream and then he comes back for a total of 48. Sometimes there's some ambiguity in the wording here, but I think that makes some sense. So we know that the water is traveling here. The speed of the water, I'm going to call that maybe V. Well, I guess we're talking about current. Okay, so let's use VC. Okay, so the velocity of the current. By the way, if you're not familiar with speed and velocity, V equals velocity, and it's kind of the same thing as speed. People who've taken physics know that there's a difference. Velocity has a direction associated, and it can be positive or negative, or speed is always positive, but that's not really important in this case. Now we know also that there's a general equation, it's called the distance equation, that distance equals speed times time. If you've never seen this before, it's a pretty sensible equation. So distance equals speed multiplied by time. So if you want to know how far you go, you take your speed and you multiply it by time. Like if you're traveling 50 kilometers per hour and you travel for 2 hours, well, you go 100 kilometers, for example. So that's how that works. Other representations of this, and the one that's actually going to be useful for us here, so I'll show you, is time equals distance over speed. This actually is what we're going to wind up using, and I'll show you why you're using that. The short answer, to be perfectly honest, is see how there's a velocity in the denominator? Well, we're going to wind up solving for your average rowing speed. So that's what we're going to wind up solving for in this equation. Now I'm just going to go ahead and call this V. Okay, so usually what you would do with a word problem, especially in any sort of physics type situation, but just in general, write down all the stuff you know. So we know that the distance you travel when you go downstream is 24 kilometers. And you know that the distance you travel when you're going upstream is 24 kilometers. Okay, so that's not very exciting. We know that the speed at which you travel downstream, so this is where it gets a little more interesting, because when you're going downstream, the water's pushing you. So your speed going down is going to be equal to your speed plus the speed of the water, which is 2. And when you're going back up, you're not going to go as fast because the speed, the velocity going upstream is going to be your speed minus 2 because the current's going to slow you down. So when we realize that, we can write that the velocity going downstream is V plus 2, and the velocity going upstream is equal to V minus 2. Okay, the other thing we can look at is time. So how long does it take to go downstream, and how long does it take to go upstream? Now, some people will have this tendency to say, well, if you're getting pushed 2 kilometers faster this way and you're getting reduced by 2 kilometers per hour that way, don't the two just kind of cancel out? And if the whole trip takes 9 hours, you should be spending 4.5 on the way down and then 4.5 on the way back up, right? And the answer is absolutely not. And if you'd like some proof of why that is, just think about an extreme case here. What if your rowing speed, what if the fastest you could row was only 2 kilometers per hour? On the way down, you'd be going 4 kilometers per hour, and on the way back, you'd be going 0 kilometers per hour. How much time would it take to complete the whole trip then? It's not 9 hours because you'd never finish. You'd never be able to get back. So there isn't really that symmetry here, and we can't use that to help us solve the problem. What we can do, though, and this is the big crux of the whole thing, is we can say that in total, we know for sure the time it takes to go up plus the time it takes to go down. We know that takes 9 hours for sure. Okay, so we just know the total time. Okay, now where do we actually go from here? We know that the time up and the time down equals 9 hours, but we're looking for the average rowing speed. So this is where this equation up here is going to be really handy. We can say that the distance you travel going up over the velocity you travel going upstream is the same as the time, right? So T is D over V. And we can do something similar here where we say D down over V down equals 9. I'm going to ditch the hours just because I don't want to deal with units right now. Okay, so do we have some numbers we can put in here? We know the distance you travel going upstream is 24, and the speed you travel upstream is going to be your speed minus 2. Similarly, you go 24 kilometers down speed at a speed of V plus 2. That's going to add to 9. And when you get to this, you should be really happy because you go, yeah, hey, I have an equation and I can solve that. Now, before we go ahead and we solve it, we notice we have a rational equation, so we've got to look at non-permissible values. So V cannot be equal to 2, and V cannot be equal to negative 2. So first of all, let's just make a little sense of this. I like these word problems because the non-permissible values start to make sense. If the speed was 2, we already talked about that, just kind of making sense. If the velocity was equal to 2, you travel at 4 kilometers down and you travel 0 back up. So this is just sort of my thinking here, right? If let's make sense of the non-permissible values. I'm just going to call this making sense of the non-permissible values. Okay, you never make it back. Never come back. If you had a situation where V was equal to negative 2, that would be like you rowing against the water because you're going backwards. And you actually don't want to be doing that either because you'd go at 0 kilometers per hour because you'd be rowing back at 2. The ocean would be pushing, or the river, sorry, would be pushing you at 2. You'd actually cancel out your motion. You wouldn't end up going anywhere. But boy, on the way back, you'd be flying at 4. Okay, so in this case, you'd never leave. So anyway, you don't necessarily have to do this part, but I think it's just fun sometimes to make sense of some of these values. And in fact, there's another, this is like a realistic domain restriction. So this just comes from the realism of the problem. Your velocity just better be bigger than 2 in general. Why is this? If you went any speed less than 2, you wouldn't ever be able to overpower the current. Must paddle faster than the current, or else you'd just never come back. Right? If the current's pushing you down at 2, you got to paddle at least bigger than 2 to get back. Okay, so we have that restriction. So this is kind of interesting. We have our non-permissible values, which are very like mathematical. Can't be 2 and can't be negative 2, but also due to the realism of the problem, you can't have velocity less than 2. And you'll notice that this is like an overall domain restriction, and this actually includes these guys, right? If you're greater than 2, well, you're already not equal to 2, and you're not equal to negative 2 either. So just keep that in mind. All right, so we're going to go ahead and we're going to continue solving this thing here. So remember, our equation was 24 over V minus 2 plus 24 over V plus 2 equals 9, and just somewhere off on the side, just keep in mind that's our domain restriction. Velocity is bigger than 2. So the way we go ahead and we solve this is we got to get those V's out of the denominator. So we're going to multiply both sides by this. So from here on out, we're multiplying both of these guys into both of those terms, and what happens, I'll skip writing, the log thing. Okay, Ray, you can write this and this and this and then this, and you cancel these out. Ugh, gets to be pretty tedious. So I'm just going to go ahead and do a little bit in my head here. So 24, the V minus 2 and the V minus 2 cancel, but the V plus 2 stays put. For this guy over here, the V plus 2 and the V plus 2 cancel, but the V minus 2 stays put. And then the other side has this. Okay, so we FOIL everything out. Let's see, plus 48, plus 24V minus 48. And this one here, this guy here is actually a difference of squares. It's V squared minus 4, so I'm just going to multiply this minus 9b squared minus 36. Save myself a little bit of the gross FOILing trouble. Okay, so we have this, and then we go ahead and we can cancel out the 48s. That's very convenient. And what we're left with is 48v equals 9b squared minus 36. Or moving everything to the right side. And I actually notice everything is divisible by 3 here. So I'm just going to divide everything by 3 just to simplify my numbers. Okay, so solving this is not a big deal. I believe this is factorable. So 3 times negative 12 is negative 36. And we've got 2 numbers that add up to negative 16. Is that possible? Yes, it is. Okay, so this becomes this, and if you see this process and you're kind of bored with it, that's good. Then you have learned what you need to learn in Math 11, that when you see a quadratic, you can just go ahead and solve it in your sleep. If you have trouble solving this, that's actually a good kind of hint for things that you want to make sure you're good with. Okay, so looking at this, we have v is equal to 6, and we have v is equal to negative 2 over 3. So I have good news and bad news for you, Jerome. This is not even possible. This is outside of the domain, and remember what this would literally mean is you're paddling backwards at v equals negative 2/3. If the speed of the current is pushing you down at 2, you never come back. Okay, so that's just not mathematically possible. But this one, this works. Okay. Now, if you just want to do a little check, so like a check here, think about it this way. If v equals 6, that means your v going downstream equals 8 kilometers per hour. Okay, so you're traveling downstream nice and quick, and the v going upstream is only going to be 4 kilometers per hour. How long does this take? The time it takes to go downstream, remember time is distance over speed, so 24 over 8, it only takes you 3 hours to go downstream. How long does it take you to go upstream? 24 kilometers, going at 4 kilometers per hour, that's 6 hours. And in total, we can see that the total time equals 9 hours, which is exactly what we wanted. Okay, so it's nice to just check these things sometimes. This is our speed, and if you want, you can say, therefore, Jerome rose at 6 kilometers per hour. Okay. All right, there we go. Next one. Ooh, lemonade. Okay, how much lemon juice must be added to 20 liters of water? Well, you guys can read. Okay, there's one thing I got to tell you right away, and you may or may not know this, but it's the concentration formula. So we're talking about a 5% fruit juice concentration. So how you figure out concentration is you think really hard about it. Are you concentrating? I'm sorry, I've shamed myself. So concentration, the concentration formula, the concentration of anything is the solute volume of solute over the total volume. So what a solute is if you have okay, oh boy, all right, I'm gonna do my best. Here's my lemon. Okay, whee, okay, there's my lemon. Okay, and you're squeezing your lemon drop, and you're putting it into a bunch of water, H2O. This is what you would call your solute, and then this is the, well, it's the solution. Okay, so the total volume is the solute over the solute plus the solution. No, sorry, let me back up a sec. This is actually not the solution, this is the solvent. Okay, I haven't done chemistry in a while, give me a break. The solute plus solvent equals solution. Anyway, that's not really the important thing here. It's the idea that when you're adding something to another thing, the concentration is how much of the stuff you added is there over the total amount of stuff. And if you add some lemon juice to some water, well, you're increasing the volume, right? So that's the total volume, is the lemon juice plus the water. So in this case, I'm going to write somewhere here, I'm going to write maybe just up top, let let X equals the volume of lemon juice in liters. So this becomes, the solute is X, that's the volume of lemon juice I put in there. That's the weirdest X I've ever drawn. Let me try that one again. And then we've got X plus, we had 20 liters of water. And now we need a 5% concentration. So we know we can just go straight to a decimal, 0.05, right? Okay, so once you've kind of put all this together, this question is not as involved as the last one. These questions generally aren't as big, but you just need to know the concentration formula. And what's kind of nice about this is it is a way of getting X on the bottom. Okay, so you have to solve this. This is actually quite an easy thing to solve. If you're going to solve this bad boy, you're going to multiply both sides by whatever it takes to get variables out of the denominator. So you're multiplying both sides by X plus 20. These guys are gone. I guess before I cross it out, I better be careful. There's an NPV. X cannot be equal to negative 20. Does that even make any sense? How do you add negative 20 liters? So sometimes things don't even make sense. A realistic domain. So again, the idea that this is a word problem, there's some realism to it. What would this be? Well, there's no limit to how much lemon juice you can add, but there is a low amount, and you can't add nothing. So X better be bigger than or equal to 0, right? You can't add negative 20 liters of lemon juice. That doesn't even make any sense. Okay, so once we've done this, we now have 0.05 times X plus 20 equals X. We go ahead and we distribute into the brackets 0.05 times X. And then what's 20 times 0.05? Isn't that just equal to 1? Okay, we'll get all the X terms on the other side, so we'll subtract this bad boy here. So we're going to end up with 0.95X, and then X is 1 divided by 0.95, and this is why I have my handy calculator over here. So we turn it on, we turn it on, we turn it on. Okay, there we go. 1 divided by 0.95, and we wind up having 1.053 or whatever. 1.053 liters. So just a little bit over 1 liter. So you take a second and just think, does this make sense? So we want a 5% fruit juice. So what a lot of people might be tempted to do is they'll say, well, 5% of 20, isn't that just 1? So why don't I just add 1 liter? But the problem with that is if you add 1 liter of lemon juice, now the total volume goes from 20 liters of water to 21 liters of water, and that's not exactly 5%. So by adding just the right amount here, we wind up getting exactly 5%. So just be careful not to fall into any trap of making this super obvious. Or, let me rephrase that. Don't fall into the trap of thinking it's really simple and obvious. Don't let your intuition trick you. All right, last question. This one's an interesting one. So Kira can mow an entire lawn in 40 minutes. When her friend Mark, I guess, work together, they can mow the lawn in 24 minutes. How long would it take Mark to be responsible for once in his life and just mow that darn lawn? All right, so what does our intuition tell us about a problem like this? First of all, if Mark and Kira were capable of working at the same speed, how long would it take to finish mowing the lawn? If Kira takes 40 minutes, well, 2 people should take 20 minutes, but Mark only reduces it down to 24 minutes, which tells me Mark is not pulling his weight. So what we need to think about here is we need to think about, first of all, what do we know? So we know that Kira mows. Now it's not so useful to think about total amounts. It's more useful to think about mows at a rate. So at a rate of, and if you have this entire lawn, and Kira mows some portion of it, well, if this is the entire lawn, so 1 lawn, she is capable of mowing the whole thing in 40 minutes. So what she can do is she can mow a section that is 1/40th of the lawn. She can mow 1/40th of the lawn in 1 minute. So her rate of work is 1/40. Mark mows at a rate of, well, what fraction of the lawn does Mark mow? So this is like Kira. Yeah, move that over here. This is Kira. Mark, he's going to mow some amount, but we've already decided he's going to mow a little bit slower than Kira, so maybe he's going to mow this patch. I actually don't know what this is. So what do you do in math when you don't know what something is? You leave it as a variable. So he mows 1/8 of the lawn in 1 minute. And that sounds like it's totally useless, but it's actually really quite useful. So in general, we have a concept here. The concept is that the work you do is equal to the rate at which you do work times the time that it takes. So if you do 1/40th of the lawn and you take 40 minutes, you get 1 lawn mowed. And that's what Kira's doing. But in this case, we've got 2 people. So Kira's work, as just like a word problem equation, we're not actually put math to it yet, plus Mark's work, we know that adds up to 1 complete lawn mowing, or 1 complete lawn. So here's the thing. So we would say her rate multiplied by the time. So the Kira's rate, let's call it K rate for lack of something better, and the M rate multiplied by the time equals 1 complete lawn. I'm just going to leave it as a 1. So her rate, she works at 1/40th of the lawn per minute, and she does it for, well, now, so when they're working together, they're doing it for 24 minutes. His rate is 1/x, and he's doing it for 24 minutes as well, and that all adds up to 1. And when you start to piece this all together, you realize that we're forming a rational equation where x is on the bottom. Now, are there any domain restrictions on x? We can see that x cannot be equal to 0. I mean, that wouldn't make any sense. Mark mows 1/0 of the lawn. That is totally nonsense. So here we go. We've got our equation. Now, solving this is actually pretty simple. The way we're going to go ahead and solve is we're going to multiply both sides by 40x. Same thing over here, 40x. Okay, so we multiply 40x, the 40 and the 40 cancel, and we're left with 24x, and when we multiply the 40x in with the other guy here, the x's cancel, and whatever 24 times 40 is. So what is 24 times 40? I could probably do this in my head, but when I'm recording, I always seem to struggle with doing basic math because I feel like everyone's watching me. Okay, so that's 960. Oh yeah, I should have been able to do that. 24 times 4 and then add a 0. Okay, well, whatever. Shame. Okay, and then 1 times 40x is there. All right, so we get 960. We'll move 24 to the other side to get 16x, and then we'll divide both sides by 16. Okay, so 96 divided by 16, that is equal to 6, so x should be 6t. Now, we didn't actually finish the problem, because the question here is, how long would it take Mark to mow the lawn on his own? What did x actually represent? X is the portion of the lawn that he mows. Portion of the lawn he mows in 1 minute, right? That's what x was. So Kira mows 1/40th of the lawn, and he mows 1/60th of the lawn in 1 minute. Therefore, here's our non-permissible value that didn't wind up coming into play. Mark mows 1/60th of the lawn. So Mark mows 1/60th of the lawn in 1 minute. Therefore, Mark would take 60 minutes. Okay. So you sort of look at that and you go, okay, well, that sort of makes sense because we already decided Mark was a little slower than Kira. Anything else big about this? Keep in mind, this was the big equation here that is governing the whole thing. Okay, so we're just finishing this here. There we go. Okay, so just the thing I really want to mention, and reinforce is that this equation, this is your everything. So this is, I'm going to call this like the work equation. And if you see this sort of idea of like sharing a division of labor or work or however you want to call it, usually you're going to want to be looking at something like that. All right, that's it. Thanks for watching. See you later.